Hi students, this is a quick tutorial including a worked example for exercise 12B and C of the Year 12 Maths General textbook. This chapter is about critical path analysis, which is something we do for those weighted activity networks. And those networks are for the planning of large projects. So here's an example in the bottom right of this slide of an example project. Now, you'll remember from 12A that the letters like A, B, C represent activities. And then in this case here, the new information to us is that there are now numbers attached to each of the edges as well. And that represents some amount of time that each activity might take. So activity A takes 1 minute in this case, activity B takes 3 minutes, activity C takes 1 minute, and so on. Now, the reason we might use one of these networks is because we have a large amount of interdependency of tasks. So for example, activity B requires activity A to be done, and activity I actually has a large list of interdependencies because it requires activity G, activity C, activity F, and activity H. Now, most of that was information covered in 12A. That's just a light refresher for you. But the terminology on the slide here is quite important for what the worked example I'm about to do. So we have critical steps or critical activities. We have the critical path and we have float time. Now, just one by one, a critical activity is any activity within a project which we cannot delay without pushing back the final finish time of the activity. Okay, so for example, if I'm building a house, I need to make sure that I've got a foundation down before I try to do things like building the walls or building the roof. Okay, so that means if I delay the finishing of the foundation, there might be a whole host of other tasks that get delayed. So when we have that kind of situation going on, we call that activity critical. So in this case, the building of the floor or the building of the foundation of the house would be a critical activity. Now, there's also a critical path going on when we have a whole host of interdependencies of tasks in our overall project. And the critical path is the list of activities in order from start to finish that must be completed as soon as they're available. Okay, so that implies the existence of tasks that don't have to be completed as soon as possible. And those are tasks that have float time. So we have critical tasks and a critical path. And those are the list of activities that must be done as soon as possible in order. And then we have tasks that aren't critical and have float time. So float time, it's just the amount of time an individual step can be delayed before pushing back the final finish time. Now there's a little typo here, but that's just meant to say also known as slack time. So you may see float time be referred to as slack time as well. Okay, here is an example network. It's actually the same network from the previous slide, but I'm going to do the actual algorithm and the process of exercise 12B and C on this slide using this example network. So there are two activities we do here, or there are two algorithms we have to do. We have to do a forward scan and a backward scan. So the forward scan is we go from start to finish and we decide cumulatively how much time must have passed to get to each juncture in the overall project. So what I mean by that is at the beginning, we have 0 time having passed before starting the rest of the project. So we put a 0 in the left side of the first vertex here, or the first node. And now we cumulatively add up the amount of time that's passed as we reach each vertex. So just remember the letters on the edges themselves, they represent the activities, and the vertices in these types of networks are just points in time where other activities have been complete. So this edge represents activity A, whereas the vertex here just represents the point in time where A is complete. Now, that's the same for all of our other vertices as we go along here. So we can do our forward scan by taking the 0 here and then cumulatively adding along the weights of each edge. So 0 plus 1 gives me 1. Okay, 1 plus 3 gives me 4. So I'm just filling in cumulatively as we go through the network. Now, the exception is when we reach a vertex that has multiple paths leading in, we have to consider all of those paths. Okay, so in this case here, it'd be 4 plus 1, which would give me 5, but I can't put that in there until I know what all of the other options are. And I'll talk about how we know which option is correct once I can compare them all. Okay, so let's go through this second path here. 0 plus 2 is obviously 2, and then 2 plus 2 would be 4. 0 plus 5 is 5, and 5 plus 1 would be 6, but I can't put that in there yet. And then finally, along the bottom path here, so this is now all 4 paths being considered, we could have 0 plus 15. So let's just go through those options again. It was 4 plus 1 is 5, 2 plus 2 is 4, 5 plus 1 is 6, and 0 plus 15 is 15. Now, out of all of those options, we have to choose the largest one. Now, the reason for that is because, like we said, these vertices represent a point in time where everything that leads up to them is finished. So if the route from activity A through B through C takes a total of 5 days or minutes or whatever this project is talking about, we could finish ABC within 5 days, okay? But 0 plus 15 is 15, okay, obviously. So what that means is out of all the activities that lead up to this vertex here, 0 plus 15 gives us the largest result. And what it means is we can't be finished all of the sets of activities A, B, C, D, H, E, F, and G. We can't be finished all of those until day 15 of the project. Okay, so that's why we have to put the largest number in, because this vertex is representing everything before it being complete, which cannot happen until day 15. Okay, from here on out, the network is pretty simple because it's just 15 plus 2 is 17, and then 17 plus 1 is 18. Okay, that is the end of the forward scan. And what we've revealed by doing that is that the overall project can be completed as early as 18 days. So that is the fastest possible time we can finish the entire project. Now, let's just be clear, that wasn't obvious just by looking at the individual activities. Because if we were to add all of the individual numbers 1, 3, 1, 2, 2, 5, 1, 15, 2, and 1, we would have gotten a longer amount of time than 18. So it's only by doing this kind of simultaneous analysis of all the things leading up to it, this forward scan that gets us to the end, that we can recognize the entire project can be completed in 18 days. Okay, so that's what our forward scan complete. We've done about half of the process here, and it has revealed to us just this one thing here, that the entire project can be completed in 18 days. I want to remind you of the one trick in the middle as well, which is when we are heading into a vertex that has multiple arrows pointing towards it, we have to consider the largest option. So I like to think of that as when I'm going forward in the network, I have to grow as much as possible. So when I'm doing my forward scan, I always have to choose the largest possible number that it could be. So now let's start our backward scan. And our backward scan is going to help us reveal float time. But for now, I'm just going to do the backward scan, and then we'll talk about how it reveals float time to us very soon. So to do our backward scan, we have to take this 18 that's on the left side of the vertex, and we have to just input it on the right side as well. So whatever is there, we're basically copying and pasting it. So we've got 18 and 18. And now we basically do backwards what we were doing before. So we're going to do 18 subtract 1, and that gives us 17. Okay, and whenever we're just heading on a straight path like this, it's going to be pretty boring. The numbers will be the same. So 18, 18, take 1, we get 17 and 17. 17, take 2 is 15. So again, we've got all the same numbers. Okay, now it's when we split up into these multiple paths that something different will actually happen. So if we do 15, subtract the 1 along C here, we get 14. And then when we do 14, take 3, we get 11, obviously. And then when we do 11, take 1, we would get 10. But again, this is a scenario where we have multiple things heading into this final vertex on the left from a backwards direction. So we can't put that 10 there. We have to consider all the paths. So let's keep doing that. 15, take 2 is 13. And then 13, take 2 would be 11. But we can't put that in for the reason I just described. 15, take 1 is 14. Okay, 14 take 5 is 9. Again, not putting that in. Have to consider all the options. So now the final option is 15 take 15, which would give us 0. Okay, and now just like when we were doing our forward scan, we were growing, so we grew as large as possible. We grew as large as possible, I should say. Now as we head backwards, we are shrinking. Okay, all the numbers are getting smaller as we go from right to left. So we have to choose the smallest number possible. Okay, so 11 take 1 was 10. 13 take 2 was 11, 14 take 5 is 9, and then the final option through the G path backwards was 15, take 15 is 0. Okay, and we get a 0 there. Now that should always be the case if you've done both your forward and backward scans correctly. You should get 0, 0 as the final vertex, or the beginning vertex, I should say. Okay, so that's our backward scan complete. What it will reveal to us is float time of each activity, as well as what the critical path might be. Okay, now before I actually sort of talk about that, I'm going to go through another few slides and then I'll come back to this network so that we can do the float time on this network. Okay, so float time works by finding the earliest start time, latest finish time, and latest start time of a particular activity, and then working with those through subtraction to work out how long that activity could be delayed for. Okay, now if we have a look at an example activity like in the bottom of the slide here, activity B takes 3 days. Okay. Now, as we've done our forward scan and our backward scan, we've populated numbers on the left and right sides of each of the vertices on either side of B. So what I want you to know is that this 1 here is actually the earliest possible start time of activity B. So that 1 is the earliest start time. And that means we can get to activity B by the time that 1 day has passed. Okay, so if we think about that, we can get to B as early as 1 day, and then B itself will take 3 days. The other interesting piece of information given to us by the numbers is the very far right number here, the 14. That is the latest finish time of B without delaying the entire project. So remember, we had an 18-day finish time for this project. Well, activity B's latest finish time is day 14. And if we fail to finish it by day 14, we'll push back the coming activities after activity B and therefore delay the 15 days. So what I'm trying to say then is activity B, we can start it as early as after 1 day has occurred. It will take 3 days, and we have to finish it within 14 days, or before the end of the 14th day, I should say. So now the way that we work with those three numbers is we do the LFT, which is actually the far right number here, subtract the duration, okay, and that's this 3 here, subtract the earliest start time of B, which is the 1 here, okay. So we're going to do the float time of B now, and by filling into that formula, basically. Now, there's another formula on this slide, but I do think that this one that I'm underlining right now is probably the most useful one for us. And think about it as far right number minus middle number minus far left number. Okay, so let's do that for activity B as listed down below. So the far right number, the latest finish time is day 14. Okay, the duration of activity B is 3 days. And then we also have to take away the earliest possible start time, which is day 1. And so when we do that, we do 14, take 3, which is 11. And then we subtract 1 and we get 10. Okay, and what that's telling me is that activity B has 10 days of float time. Okay, and as we know, the definition of float time means that's the amount of time it could be delayed for before the entire project gets delayed. So activity B is not critical. It doesn't have a float time of 0, so it's not critical, which means we can delay it for any amount of time up to 10 days. And that's the information that the backward scan has really revealed to us, because we needed this 14 here, which only happened in our backward scan in order for us to do the float time calculation, which we've just done. Okay, and I will go back to the previous network soon so that we can see that play out even more. Okay, something to consider for our float time too, just before the end here, is if float time is positive, just like the 10 days we received for B just now, we're saying the activity can be delayed by an amount of time equal to its float time. So therefore the activity is not critical, and like we said for B, that means it can be delayed for 10 days. If float time is 0, that means the activity can't be delayed at all, because if we delay it, we'll delay the overall finish time. And that would mean therefore that the activity itself is critical, okay? And it could be part of the critical path therefore. Okay, one last exception to this is if float time is negative. So if we do the far right number minus the far left number and minus the duration of the activity, and we get a negative number, that means we've made a mistake. Okay, we can never have a negative amount of float time. It just wouldn't make sense.